Have you ever wondered how navigation systems like Google Maps work? Continue watching this video to discover the data structures and algorithms behind these wonderful apps. We will break this down using a small map with some houses, various roads and intersections, and to further complicate things, we'll make this road one way. First things first, we need a way to store this data, and to do that, we need to understand graphs. Graphs in computer science are data structures that consist of nodes, also known as vertices, and edges, which connect these nodes. Graphs can be characterized as directed or undirected, and as weighted or unweighted. In an undirected graph, an edge between two nodes means you can traverse it in either direction. You can go from A to B, and from B to A. In contrast, a directed graph uses arrows to indicate the direction of travel. You may only be able to go from A to B, or from B to A, or sometimes there may be two directed edges, one in each direction. An unweighted graph simply shows whether a connection between two nodes exists or not. However, in a weighted graph, each edge has a cost or weight associated with traversing it. The meaning of this weight depends on the context. It might represent the time taken to travel between the nodes, the distance between them, or any other meaning relevant to your scenario. Graphs can also combine these properties. For example, consider this graph. If you said that it's a directed weighted graph, where going from A to B has a weight of 3, and going from B to A has a weight of 2, then you would be correct. Okay, so now you understand graphs, but how do we store them when programming? Well, there are two main approaches, an adjacency matrix or an adjacency list. With an adjacency matrix, we use a two-dimensional matrix and assign a row and column to each node. Then if we have an unweighted graph, we can fill in the matrix with zeros and ones, where zeros indicate no edge between the row node and the column node, and where ones do indicate an edge between the nodes. For instance, for this unweighted directed graph, we put a 1 in row A column C, a 1 in row B column A 1 in row B column C, a 1 in row C column B, a 1 in row C column D, a 1 in row D column C, and fill the rest with zeros. If our graph was weighted, then we can simply replace the ones with the weight of the edges like so. Now, adjacency lists are slightly different. In adjacency lists, we store a list of all our nodes, and then for each node, we store another list of all the nodes it has an edge to. For instance, the adjacency list for our unweighted directed graph from before would look like this, where you can see there is a path from node A to node C, a path from node B to node A, and a path from node B to node C, a path from node C to nodes B and D, and a path from node D to node C. Now, if our graph is weighted, then we can store those weights in the list like so. And now we can see that there is an edge from node A to node C with a weight of 4 and so forth. Now you may be wondering when to use an adjacency matrix versus an adjacency list. Let's take our graph and matrix from earlier. Since we only need to know whether an edge exists between two nodes or not, we don't care about all these zeros. This is different to our adjacency list, where we only store information about existing edges. Therefore, our adjacency list is more space efficient. However, the benefit of an adjacency matrix is that it is generally quicker to check if an edge exists between two nodes than when using an adjacency list. So we want to use an adjacency matrix when the number of zeros in our matrix is minimized, which occurs when each node in the graph connects to every other node. This is called a dense graph. Conversely, when each node only connects to a few other nodes, it is called a sparse graph. Therefore, as a general rule of thumb, we use an adjacency matrix for dense graphs and adjacency lists for sparse graphs. With all that explained, we can now go back to our map from the start and add some extra information, including the distances and speed limits of the roads. We can now convert it into a graph by turning all the houses and intersections into nodes, and the roads will become directed weighted edges. For the weights of the road, we will use the time taken to traverse it, which we can calculate by dividing the distance of the road by its speed limit. We will store all this raw map data in a Python dictionary with the source and destination nodes as the key, and another dictionary containing the distance and speed limit as the value. Then, since our map is a sparse, directed weighted graph, we will use this data to create an adjacency list. We start by creating a function that takes this data and initializes an empty dictionary. Then we loop through all the items in our map data dictionary. For each edge, we will calculate the weight representing the time taken to traverse the edge by dividing the distance with the speed limit. We will then check if the start node is in our dictionary. If it is not, we will add it as a key and create another empty dictionary for the value. We then add the end node along with the weight to this subdictionary for the start node by using the end node as the key and the weight as the value. And to check that this is correct, we can print out our adjacency list. That looks good, and now that we have our adjacency list storing our graph, we need a way to find the quickest path from one node to another. One of the most popular algorithms for this is Dijkstra's algorithm, which calculates the shortest path from a source node to all other nodes in the graph. In this graph, let's assume the weights mean the time taken to travel along the edge in seconds. To start, we pick our source node and we set the time taken to travel to this node to 0, as we are already there. We then set the time to travel to all other nodes to infinity, as we don't know how long it takes to travel to them from our source node. We also need to maintain a list of all the nodes we have visited. From our starting node A, we explore the time taken to travel to all its unvisited neighbours, and update the travel time using the weights of the edges to that neighbour. In this case, it takes a weight of 6 to get from A to B, and a weight of 1 to get from A to C. We also store the node that we travelled from, in this case node A. Once this is done, we can mark our source node as visited and move on to a new node that we haven't yet visited. To do this, we pick the next node with the smallest current travel time, which is currently node C with a travel time of 1. We then once again explore each unvisited neighbour and calculate the time to that neighbour by adding the weight of the edge to the travel time of the currently visited node. If the travel time is less than the currently recorded travel time for that neighbour, we update it and record the new node we travelled from. If the travel time is not less than the currently recorded time, then we do nothing. So let's do that. From node C, we can travel to node B with a weight of 3, and we add that to the travel time for node C, which is 1. So now we know we can get from A to B with a weight of 4 by going through node C. Now 4 is less than the current recorded time for B, which is 6, so we update B with 4 and record that we came from node C. From C, we can also travel to D with a weight of 4 plus C's travel time, which is 5. And from C to E with a weight of 5 plus C's travel time, which is 6. We now mark C as visited. We then continue to repeat the two steps of picking the next node with the shortest travel time and exploring its unvisited neighbours until we have visited our destination node, in which case we can terminate the algorithm early, or we can continue to let the algorithm run until we have visited all the nodes. And for completeness, we will do just that. The next node with the smallest travel time is B, so we move on to B, and since it does not have any unvisited neighbours, we can automatically mark B as visited and move on to the next node with the smallest travel time, which is node D. From node D, we can travel to node E with a weight of 2, plus the travel time for node D, which is 7. Now 7 is not less than the currently recorded travel time for node E, which is 6, so we do nothing. D is now visited, and we only have node E left, which does not have any unvisited neighbours, so we mark that as visited and our algorithm ends. Now we know the shortest time from our source node to every other node in the graph, and to find the path to a particular destination node, we use the previous node values to travel backwards from our destination node to the source node and then reverse that path. For instance, we know that we can get from A to B in 4 seconds, so starting at B, the previous node is C, then looking at C, the previous node is A, so our path is B to C, C to A, and if we reverse this, we get our path from the source node to our destination node. Now some important things to note about Dijkstra's algorithm is that it may produce incorrect results in graphs that have negative edge weights. Also, it can be inefficient in large graphs due to exploring a path to every node. To combat this, there is another algorithm called A*, which extends Dijkstra's algorithm with a heuristic to trim the search space. However, that can be a topic for another video, and since our graph is only small, I will stick to Dijkstra's algorithm. To implement this algorithm in Python, we will define a function that takes our graph as an adjacency list, the start node and the end node. We will then initialize 4 variables. The first is a dictionary to store all our nodes and their corresponding travel times. Each node's travel time will be initialized to infinity, except for our starting node, which will be initialized to 0. The second variable is another dictionary, which will hold all our nodes and their corresponding previous node, which will allow us to recreate the path at the end. The third variable is a priority queue, which we'll use to store the unvisited nodes and their current recorded travel time, and we'll initialize this by adding the start node with a value of 0. The reason we use a priority queue is so that we can efficiently select the next node with the current shortest travel time when moving from node to node. Fortunately, Python has a standard module that implements priority queues, so we don't have to do that ourselves. If you want a video on priority queues and their various implementations, let me know in the comments. The final variable is an empty set that will contain all the nodes we have visited. Now that we have those variables initialized, we can move on to the main part of the algorithm, which goes like this. While there are nodes in our priority queue, get the node with the current smallest travel time. If that node is our destination node, then we have found the smallest travel time and can exit the while loop. Otherwise, check if we have already visited that node. If we have, we can continue to the next node. Otherwise, loop through each neighbor for this node. If that neighbor has been visited, move on to the next neighbor. Otherwise, calculate the travel time to that neighbor using the current node's travel time and the edge weight. If that travel time is smaller than the currently recorded travel time in our travel time dictionary, then we update our travel time dictionary, update our predecessor dictionary, and add that node with this new travel time to the queue. Once we have explored all the neighbors, mark the current node as visited. Once we have exited our while loop, we check if the travel time to our destination node is infinite. If it is, then there can't be a path from our source node to our destination node. If not, then we can reconstruct the shortest path by starting at our destination node and moving through our predecessor dictionary until we have reached a node with a value none, which indicates our starting node. We can then return the reverse of this path and the travel time to the end node. Now that we have our adjacency list and our shortest path algorithm, let's bring back our map from the start and find the shortest path from house 1 to house 4. And we can see that the shortest path from house 1 to house 4 takes 0.109 hours, or 6 minutes and 32 seconds, and the path to follow is H1 to C2, C2 to I2, I2 to I4, I4 to H3, H3 to I3, and finally I3 to H4. How cool is that? Now this is a very simplified version, and in reality, applications like Google Maps do this on a global scale, and have a plethora of other systems to help provide all the unique features and enhancements you see. But the purpose of this video was to give you an insight into the core data structures and algorithms that power the technology we take for granted every day. Thank you for watching, and I'll see you in the next one.